Welcome to Unit 3. Here we're looking at work and energy. This is again for both double award and separate science, WJEC Year 11 course. So what we're looking at in this, so we're going to look at defining what do we mean by work, what do we mean by energy. We're going to discuss the energy changes that happen in different objects. We're going to be able to calculate kinetic energy of an object. We're going to calculate the gravitational potential energy of an object. We're going to look at Hooke's law, and then we're going to talk about the work done or the energy stored in a spring. And then finally, this is where, if you've been following these videos, said back in Unit 1, things done slightly out of order. The rest of this unit has the car safety stuff in it. So we have stopping distances, how we make cars efficient, and how we make cars safer. So some of that topic, especially the stopping distances, is technically part of Unit 1, but if you don't understand energy, it becomes, especially kinetic energy, it's not that clear as to why things happen in that, so that's why it's here. Okay, so here we have our useful links. Again, if you're watching this on YouTube, they'll be in the description below. If you're watching this on PowerPoint, they will be on, you can just click them off here. Okay, so on to our first bit of content then. So work and energy. So key thing to remember, which you probably have touched on before, is the conservation of energy, that we can't create it or destroy it. We only transfer it though from one form to another. So what does that mean? It means that we've got a set amount of energy. In any given system we have a set amount of energy, and we just convert it from one form to another. So whatever energy we start with, we'll have left at the end. Now work is a measure of energy, and we talk about work as being energy transferred. Alright, and we measure that in joules just like energy. Now, the main way that work is done, and you might have heard of work done, is by a force moving an object. So work done is force times the distance moved in the direction of that force. Alright, so force measured in newtons and distance measured in meters. So we get this formula, W equals FD. Work is force times distance. Now, kinetic energy. Now, any object moving has kinetic energy, and the amount of kinetic energy that you have is equal to a half times your mass times your speed squared. And that speed squared is important. If you double your speed, you quadruple your kinetic energy. Speed velocity doesn't matter because you're squaring it, that sign will go away, so it doesn't matter. Now if we do work on an object to make it go faster, where that work will be done, it will be transferring energy into kinetic energy. So we can think of sometimes as work done as a change in kinetic energy if an object's moving faster. Okay, so gravitational potential energy then. So if we raise an object up off a surface, it gains gravitational potential energy. And this is work we've done against gravity. So this means if we apply our work done formula, work done is force times distance, and the fact that we know that the force of gravity is your mass times your gravitational field strength or your weight, we get the formula then that change in gravitational potential energy is weight times change in height, or change in gravitational potential energy is mg times your change in height. Now you'll notice here we've got this funny triangle symbol. Now remember, a triangle symbol like that just means changing. So wherever you see that triangle symbol, it just means changing. It means take the difference between what you started with and what you finished with. Okay, so Hooke's law then. So another form, very common form of energy that we deal with is elastic potential energy, and this is where Hooke's law comes in. So we can also do work deforming an object, so stretching it or squashing it. And this will change, like I said, the amount of elastic potential or strain potential in the object. Now, A couple of key words we've got here. First one we've got is extension. Extension, by extension what we mean is change in length. So if you've got no change in length, then your extension is 0. Common mistake students make when they deal with questions on Hooke's law is they use the length of the object, not the changing length. Now what Hooke's law says is that the force applied to a spring is proportional to the extension. Okay, he also found that if you continue to stretch a spring, you get to a point where it no longer behaves like a spring and starts just stretching out. And we call this the limit of proportionality, where basically Hooke's law is no longer obeyed. The extension will not be proportional to the force that you apply to that spring. Now Hooke's law can be written as an equation. F, the force you apply to the spring, is Kx, where K is the stiffness or the spring constant. The bigger K is, the stiffer your spring, the more force you've got to apply to stretch the same distance. Now, if we draw a graph of this, like below me, we get a graph of force against extension. And if we go, well, if we do force times extension, force times the distance is work done. So the area in here, green, is the work done stretching the spring, or the energy stored in the spring. And you can see it's a triangle. Area of a triangle is a half base times height. So that gives us our equation for the work done stretching a spring being a half F times X. Now you could take this one step further and you can substitute in Hooke's law and you get that the work done stretching a spring is also a half kx squared. So if you're not given the force in a question, then you can use this format here if you're given the spring constant without having to do a separate equation to work out the force. Now you are also expected to know how to combine springs. Okay, and generally we can combine springs in one of two ways. We can combine them in series or we can combine them in parallel. Okay, if we combine them in series, we connect a spring end to end. And springs in series will appear weaker than just one spring. Why? Because each spring is having to support the load, so they both stretch the same amount as though they were just one spring, which means overall we've got double the extension, so we've got half the spring or half the stiffness we started with. If we put them in parallel, however, then they share the load. Okay, parallel means the springs are side by side and they share the load. This means that they appear stronger than just one spring. Okay, so if you have two springs in parallel, you're adding those spring constants up together. Okay, and you're ending up with a stiffer spring. Okay, so transferring energy. So we've already touched on the fact that energy cannot be created or destroyed, but instead has to be transferred from one form to another. Now the classic questions that they ask about things like a bouncing ball. Okay, so if we pick up a bouncing ball, as we pick it up, it has gravitational potential energy. As that ball drops, that gravitational potential energy is converted into kinetic energy, all the way to when the ball hits the floor. Just as it hits the floor, all of the gravitational potential energy will have gone and it will have kinetic energy. As the ball hits the floor, it squashes. So some of its kinetic energy is converted into elastic energy. When that ball then rebounds, some of that energy goes back into kinetic and the ball goes flying up. Now, in an ideal situation, a ball will just always bounce up to the same height every single time. However, we don't deal with ideal situations in the real world. We deal with real world situations. And every time you bounce a ball, some of that energy is lost. Some of it is wasted. Most commonly as heat and as sound. Okay, and you can see that here, that the total energy of this ball is dropping with every bounce. Now, where's that energy going? That energy is going mostly into the ground. It's going to heat the ground up or going into sound in the air. So you can see here that as the ball energy drops, the ground energy rises, so the total energy of this system always stays the same. Okay, now on to cars then. So, stopping a car. To stop any car, we are converting its kinetic energy into mostly heat. That's what brakes do, via friction. So work done is the friction of the brakes. They convert the kinetic energy into heat, so much so that if you watch race cars at night, you can see their brakes actually glow red. They get red hot. Now, it takes time to do this though. We can't, if we were to convert all of that energy from kinetic energy to heat in one go, it would just be catastrophic for the car. Your brakes would get really hot, and it would be really bad for the passengers inside. So instead, we have to do it over a period of time. So what this means is that cars travel a distance whilst you're stopping. Okay, and this leads us to three definitions. First one, stopping distance. So stopping distance is the total distance to stop a car. And that's the thinking distance plus the braking distance. The thinking distance is the distance travelled whilst the driver is reacting to a hazard. So whilst someone steps out into the road, you're going, oh, I need to put my foot on the brakes, and the time it takes to do so. But it takes time, you're travelling a distance, so you travel a distance. Now, I've just made that mistake. Please, please, please take care with this. Loads of students get this wrong. When they're asked what thinking distance is, they start talking about reaction time. And it's not. It's the distance you travel whilst you are reacting. Okay, so don't say it's the time it takes. No, it's the distance you travel whilst you are reacting. Now, braking distance is the distance you travel actually whilst the brakes are applied. Okay, now, thinking distance depends on two things. Depends on the speed you're going and your reaction time. Yeah, distance being speed times time. So it means that thinking distance is directly proportional to your speed. So here, it's the pink line just here, and it's a straight line through the origin. Now, braking distance depends on the kinetic energy that your brakes are having to convert. So therefore, it is proportional to speed squared, which is why the braking distance is a curve. And if you look, doubling the speed quadruples the distance you travel because of that speed squared term. Now, when it comes to stopping cars, you're expected to know what factors or what things affect what. So, anything that affects the friction between the car and the road, or the wheel and the brakes and the brake discs or brake drums, is going to affect braking distance. So that's things like the mass of the car, because that gives you more energy to stop, means that you're going to need to have more work done. Obviously, the speed of the car is discussed. The road condition, if the road is slippery, then things like snow, ice, snow about 10 times as far, rain's about 4 times as far. Brake condition, if you've got brand new brakes, you're going to stop a lot quicker than if you've got warm brakes. Tyres, if you've got bald tyres and you're trying to stop when it's wet, you're going to take an awful lot longer to stop. Likewise, if you've got overinflated tyres, you've got less tyre on the road, it takes you further to stop because you've got less grip. Anything that affects reaction times is going to affect thinking distance. So things like drugs and alcohol, affect a driver's reaction times. Weather, but weather that obscures the driver's vision. Yes, you're going to react in the same time, but you're not going to get that clue as soon. So that affects your reaction distance. Tiredness affects your reactions. And again, speed of the car, as discussed before, you've got to time your reaction. Speed times time equals distance. So the faster you go, the further your thinking distance. Now, speed limits. There's been a couple of questions as why do we have speed limits? And it's related to these stopping distances. So by making cars go slower, they stop in shorter distances. Okay, also by going slower, you have less energy in impact. If you do the maths, going between 30 and 40 miles an hour, 40 miles an hour has roughly double the energy of 30 miles an hour. This is why you've seen those adverts that say, you know, you're far likely to kill someone at 40 than you are at 30. Geography is a big thing that decides speed limits. So, you know, if you've got a school that's 20 meters, as it says here, from a blind bend, then they're going to put a much lower speed limit, because especially 20 miles an hour, at 20 miles an hour, the overall stopping distance is well below 20 meters, about 15, 16 meters off the top of my head. So that means that as a driver comes around the corner, if a kid steps out into the road, the drivers should have enough time to stop and not hit the kids. Again, I've seen a question on that. So we have speed limits because of these braking distances, so that cars hopefully can stop. If they're doing below the speed limit, they can stop in a short enough distance to not hit anything. Okay, making cars efficient. There are 4 ways to make cars more efficient. That is, make them more aerodynamic, make sure that they are more streamlined. Okay, so anything that's going to affect the ability of the car to pass through the air is going to affect your efficiency of a car. Now, rolling resistance is all about, basically, as your tyres roll round, they squash and they bend and they flex. This wastes energy. So if you can reduce this, then you reduce energy losses. So if you have tyres that are narrower, they don't bend, don't flex as much, then you have lower rolling resistance. Idling losses. So this is where, if your engine's running, you're going nowhere, it's just wasting energy. So if you have start-stop technologies, that reduces idling losses. I was reading a thing earlier about UPS in America. If you know about driving in America, you can turn left on a red light on quite a lot of junctions, as long as it's safe to do so. Sorry, turn right, sorry, because they drive on the other side of the road. So you can turn right. It would be turn left in the UK. But you can turn right, even if it's a red light. And so they instruct their lorries, because a lot of American cities are built on a grid system. If you take 3 right turns, it's the same as going left. So they instruct their lorries basically to just do right turns, and it saves them an awful lot of fuel through idling losses. And in fact, it's quicker because they're not having to stop at traffic lights. And the final one is inertial losses. So we spoke about inertia in Unit 2 being to do with mass. That, you know, mass is not wanting to change their motion. So if you can reduce the amount of mass that you're having to move, then you're going to reduce your inertial losses. So things like carrying excess weight in the boot, you know, just stuff that you're never going to need, don't put it in your boot, take it out. That will definitely improve the efficiency of your car. Okay, now making cars safer. Pretty much all car safety things, well, they come to 2 things. One, they either are about reducing distractions. So something like electric windows is all about reducing distractions, that you're not having to really crank a window, so you shouldn't get distracted by that. Controls on the radio controls on your driving wheel, about reducing your distractions. But most actual safety features, what we call an active feature in a car, are either about increasing the time it takes the car to stop in a collision, or increasing the distance the car stops over. And some do both, and you can view it from either way. Now, why does time matter? Well, if you're doing separate science, this is the one for you, because we'll talk about momentum. Basically, we come across this equation that force is change in momentum divided by time. So if you divide anything, change in momentum is going to be your mass times your change in speed. So yes, you can make a car safer by making them go slower. Definitely, that's true. But if we assume that the speed is fixed, if we increase the time, dividing by a bigger number means that we reduce the force. Yeah, so here, by taking a longer time to stop, we get less force, and it's the force that's actually going to do damage to us in a car. Now, if we think about a distance argument, well, our formula for work done is force times distance. So if we rearrange that to say force is work done divided by distance, work done is going to be changing kinetic energy, is going to be related to the speed, nothing we can do about that. But if we divide by a bigger number, same argument as before, we're going to reduce the force. Okay, so that's where most car safety features work. Things like crumple zones. Yeah, crumple zones mean that bit crumples. It increases the time or increases the distance the car stops over. Okay, so that's the key principles to know about when it comes to making cars safer. Okay, so over to you then. So remember, if you're on the presentation, stop the presentation now, double click this document, you can open it up. If you're watching this on YouTube, I'll put a link to this document in the comment in the description below. You can have a go at these questions. Pause the video now, and when you're ready to have a look at the review, move on.
Okay, so let's go through these questions. Hopefully you've watched this, not watched this, so you've completed your questions before watching this. I warn you, this is going to be another long session. There's 25 pages worth of questions here. So you might want to watch it in a couple of goes. So first thing, we got road traffic accidents occur, blah, 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 gives us an equation, shows us some data, asks us to complete the table. This sort of question, pardon me, could quite easily be missed. So the first number here, this 18, the way to work that out is you look at the pattern. It's +3 each time, work out the pattern. And then the stopping distance, well, if you looked, this bottom number is this one plus this one. So we have to add these two together and we get 74. Pardon me. Describe how the worn tyres affect distances. So worn tyres are going to have no effect on thinking distance. Yeah, because they affect the car. So what they're going to do is they're going to increase the braking distance. Now, a mobile phone is going to all about affecting the driver. So it's going to increase your thinking distance. But it's going to have no effect on the braking distance. Yeah, braking distance all about how well the car can actually stop. Okay, right. So we're now on to question 3. And we've got about some trampoline, and you can read all the stuff. Definitely read it. There's plenty there to get stuff in. Use an equation to calculate the size of the resultant force required to produce this acceleration. I feel like we've missed a page. We have. We've got a page missing here. Well, we will miss that out. Sorry, that question's not there, so we'll miss that out. Right. So foundation 19 now. Okay, so this question was a horrible. Well, no, yeah, this question was a difficult question for a lot of students. So calculate the mass of the woman. She's got a weight of 550, so your mass is going to be your weight divided by 10, which is 55 kilograms. Okay, we've got to convert 5.6 kilojoules into joules, so that's 5,600 joules. Work out the mean force. So the mean force is going to be the work done, 5,600 divided by the distance that you've got, 2.8, and the mean force is going to be 2,000 newtons. It suggested that it would be safer if the airbag were filled with water. The distance to stop the same woman would be 0.8 instead of 2.8. Explain, without further calculation, whether you agree with this suggestion. When we look at this formula, force is work done over distance. Now, if we stop her over 0.8, distance has gone down, which means force must go up. Okay, so distance decreases, force increases. Oh, sorry, because we're falling, it's the same mass, and the work stays the same, and the work done stays the same. So disagree. And the 3 marks here are basically 1 for saying the work done stays the same, 1 for saying the force decreases, 1 saying distance decreases, 1 saying force increases, and disagree needs to be there to get all 3 marks. Right, so quickly on to the separate papers, so separate foundation. Okay, so question 6. Right, name the energy a car possesses due to its motion. So if it's motion, it's got to be kinetic energy. The work done is going to be the force no, not the force, sorry, we're told it's travelling with that amount of energy. The work done must be that energy for 1 mark. Reading too much into the question. To work out the distance, we are going to do the work done, 127,500, divided by the force, 500,000, and that gives us a distance equal to 0.255 meters. State 1 feature designed to keep the driver safe. So you could talk about crumple zones. You could talk about seat belts. Could talk about airbags. But how do they do? Well, they decrease the force. And how do they do it? By increasing the distance travelled, by increasing distance by increasing distance, or increasing stopping distance is even better there. Yeah, they basically mean that you stop over a greater distance, decreases the force. Okay, right, so we've got another spring question. 2019 foundation, there we are, right. Question 6. Okay, so use the graph to determine the unstretched spring length. So that's going to be there. So that's 10 centimeters. When we apply no force, that'll be the unstretched. Use the graph to calculate the extension when we apply 2.5 newtons. So 2.5 newtons gets us to 35 minus 10 is an extension of 25. Because remember, extension's how far that spring stretches. Okay, calculate the spring constant. So that's going to be, as we just worked it out, 2.5 divided by 25. Would help if I did this the right way around, sorry. Let's just get rid of all of that. Let's do that again. Force was 2.5 and the distance is 0.25 because they want it in meters, so we have to change that to being into meters, and that gives a value of 10. Right, 2 identical springs connected in parallel. It tells us here the spring constant is doubled, so what that's going to do is that is going to give us a much stronger spring, and in fact it's going to double the spring. So what they're expecting is a line that is twice as steep to get that mark. So we're going to start from there, and it's going to be twice as steep. So it's going to finish 4 at 25 rather than at 50, which is twice as hang on, no, scrap what I've just did. Sorry, it's still going to be there. It's just going to be twice as steep, which means that it's going to get to 30. Yeah, because the extension has doubled. Okay, so this has done for 4 newtons. It's got an extension of 40. So instead, it's going to be 20. So it's going to go up to there. So it's got to be twice as steep. Okay, now we've got a stopping distance question. Okay, so suggested that thinking distance and braking distance are directly proportional to speed. Explain whether this suggestion is true or not. So directly proportional means straight line through the origin. So for thinking distance, true as straight line through origin. However, for braking, not true, as the line is curved. And it's 1 mark for each of those sentences. Okay, use the information to calculate thinking time of a driver driving at 40 miles an hour. So we look at this and we get that 40 miles per hour we come across is there. So that gives us a reading of 12 meters. So we have 12 divided by, now we don't use 40, instead we use 18. So 12 divided by 18, which is 0.67. Now take care in your calculators, because that's probably 0.6 reoccurring. So we round, don't forget we need to round that. Then we've got to work out the overall stopping distance. So we do this by adding the 2 points up. So that's 0, 12, 22, 36, 72, and 95. There is a little bit of leeway, and you can get one wrong and still get all 2 marks. Use the data to plot the points and draw a line to show how the overall stopping distance depends on speed. So you're basically going to plot those points on that graph and you're going to get a curve. And for 3 marks, it's basically 2 marks for your points. If you get all 5 points, it's 2 marks and 1 mark for your line. I'm not going to do that now because it takes a lot of time on the computer and you don't really get a good thing. So here we are. So they've reduced speed limits outside of school from 30 to 20. And the entrance to the school is situated 15 meters after a bend. So if we look at our thing here, if we look, the overall stopping distance at 30 is 22 meters. So at 30 miles per hour, stopping distance is 22 meters. However, at 20 miles per hour, it's only 12. Okay, now 12 is less than 15, so less chance of a collision. So the 3 marks are basically 1 for going, oh, it's 22 if it was 30, 1 for saying it's 12 if it's 20, and the other mark is for this sentence down here, something saying that 12 is short enough that you can come around the corner and stop in time, so you shouldn't hit any kids. Right, so on to the higher papers. Okay, so we've got this question. Now we did this question before, haven't we? We've already done this question. Yeah, already done that question. So if you want to have a look at this question, go back to the previous video and or the previous presentation, and it's on there. Not going to do it again in this one. Right, question 5. Okay, almost all cars rely on fossil fuels. Bit of information. Car uses 10 litres of fuel per week. Calculate the mean mass of CO2 emitted by the car in a year. Okay, so right then. So 10 litres of fuel per week. Okay, so on average, it's going to do 316 kilometres per week, which will equal 1,642 kilometres per year. Okay, and each kilometre produces that much CO2. Therefore, we have 1,462.4 kilograms of CO2. So what I've done here is I've done, right, 10 litres of fuel per week. We do on average that fuel economy, so that gives us that many a week, multiplied by 52 to give us that many in a year, and then we've multiplied that number by 8.9 times 10 to the minus 2 to give us the kilograms of CO2. Energy can be lost from cars in a variety of ways, such as inertial, state design features that manufacturers can use to reduce each of these losses. So, if we start with idling, because I think that's the easiest one. Now, it just says state. We don't need to explain in any way. So, idling losses, that's stop-start engines. Yeah, so you may notice that now with a lot of cars that if you stop at a set of lights, put your handbrake on, take your foot off the clutch, take it out of gear, the engine will cut off. Okay, inertial losses. Inertia, all about weight, all about mass. So we use low mass materials. And then what we got, rolling resistance. So to overcome rolling resistance, the big way you see it is they just use narrower tyres. You basically have a smaller tyre print on the ground, you get less rolling resistance. During the journey, the car slows from 30 to 10 meters per second. Using the equation for page 2, calculate how much electrical energy is transferred to the battery if regenerative braking process is used at its maximum energy transfer. So the maximum energy transfer is 60%. So if we work out how much energy is being wasted, okay, now we can't just do the 20 squared and work out what the energy is there because it's 20 squared. So what we have to do, if we have to work out the kinetic energy at 30 meters per second, which works out to be 522,000, and then we work it out at 10 meters per second, which works out to be 58,000. So the change in energy is going to be 464,000 joules. Okay. Now the actual energy transferred is going to be, the energy transferred is only going to be 60% of that, equals that times 0.6, which is 278,400. Okay, and that's how much electrical energy is going to be transferred to our battery. Okay, right, higher 2019. Okay, so we'll look at this question now. So higher 2019, and it's question 2. That's not the 2019 higher paper, that's foundation. Let's get the right paper. Oh. Interesting. That's not the right mark scheme then, is it? Let me just check that it's not the separate one and I've mislabeled it. No, it's not there. Ah, that's interesting. Oh well, we haven't got the mark scheme for this one. Right. Oh, gone on to the wrong thing. Right, let's get back to where we were. Sorry about this. This video is long enough without me messing up. Right. Okay, so manufacturers test new cars. No, definitely not that. Right. Test new cars on a level track in order to find out how long it takes them to accelerate 60 miles an hour. So this question is one that we've already done. It would help if I had the right question up. It's this one. So let's just have one last look through my mark schemes. And just check that it's not because I've been looking at the wrong question. No. Okay. So Newton's third law of motion, okay, for us is going to be if body A exerts a force on body B, B exerts an equal but opposite or opposite force on A. Explain how it applies to the car and the wall in this collision. Okay, so basically how it applies to this is that the force the car exerts on the wall. Are we given that force? No. The wall pushes back with the same force. Okay, right. I've got the mark scheme now. It's question 1, not question 2. Or at least on the mark scheme it's question 1. It might be a mistake on the mark scheme. Right, use the graph opposite and an equation on page 2 to calculate the mean resultant force on the dummy during of mass 85 kilograms during the collision. So what we need to do is work out their average deceleration, okay, which is going to be 15 divided by whatever that time is. So it will be 15 divided by 0.028, which is 535.7. Now you can put the minus signs in if you like, but it just talks about the direction. And the force is going to be 85 multiplied by your answer there, and that will give you 46,000 newtons. Okay, so you use the graph opposite to explain whether the resultant force is constant during the collision. Well, the gradient is not constant. Okay, which shows the force increases, because it gets steeper, that line. So shows the force increases through the process. Yeah, if you look at this graph, this line gets steeper, which means the acceleration gets greater, which means the force increases. Explain in terms of work how crumple zones would improve the safety of a head-on collision. So, the force is work done divided by distance. Okay, now if we think about it, crumple zones increase distance, so the force is smaller. Yeah, work done's got to stay the same, so those are what we get the marks for there. Right, question 5. That's interesting. I don't seem to have the rest of this mark scheme. Okay, I know why. Okay, write down the spring that can withstand a maximum load of 1.2 newtons and has a maximum extension close to 14 millimeters. Okay, so we can forget about B because it's got to be at least 1.2, and we want a difference, we want a maximum difference of 14 between these numbers. So if you look just roughly without doing a calculator, that's roughly 7, that's roughly 7, that's 11, that's roughly 14, that's 7, and the bottom one is going to be 13. In fact, nearer 12. So that's got to be spring D. Express the spring constant A in standard units. So, of A, spring constant, this is newtons per millimetre. So if you think about it, the newtons per metre, you're going to be 1,000 times bigger, which is going to be 170. Okay, so chosen spring C. Work out the energy stored when it's at its maximum length. So the energy stored in a spring is a half Fx or, as we haven't got F, it's going to be a half Kx squared because we've got K and we've got X. So let's put those numbers in. So with spring C, so we know K is going to be, so half, we know K is going to be 120 because we multiply, remember, like we just done here, this number by 1,000. Now X in this case is going to be the extension, which is going to be this one, take away this one, which if we work it out is 10.7 millimeters. So we get the energy stored in our spring to be 0.0068694 or 6.9 times 10 to the minus 3 joules. Work out theoretical height the ball could gain, so therefore we're going to use E equals mgh. H is going to be E over mg, so it's going to be our 6.9 times 10 to the minus 3 over 15 times 10 to the minus 3 multiplied by 10. That minus 3's cancel, that's going to help us a little bit, and that is going to get us a height of 0.04 45796 meters. So what's that, 5 centimeters approximately? Okay, data logger is used to monitor the motion of the ball as it rises from the spring. The graph is automatically produced and showing the velocity as we have there. Student states that the height the ball reached is different from what you've calculated. Show that the statement is true. So if we've got velocity time graph, the distance that ball travelled is going to be the area underneath it. So that is going to be a half, because it's a triangle, times the base, which is 0.09, sorry, times the height, which is 0.9, which is 0.0405, okay, which is going to be different. So it's 1 mark for that, 1 mark for that, but you have to include the statement. Now the next question is, why is it different? Well, we're going to some of the stored energy in spring lost to heat. Yeah, because we're going to have some heat on this as the spring, and when does that happen? The spring retracts. One change that enabled the ball to reach a greater height in this experiment. We can't stretch it any further, so we just want a stiffer spring. So use spring that is stiffer. Or bigger spring constant, but spring that is stiffer will do there. Okay, so Welsh company, we got a toy here with a spring, and again, so we're plotting a graph, 4 marks plotting a graph. So what we're going to be asked to do is to plot this graph. When we plot this graph, first job is to do the axes. Now, I'm not going to spend time now plotting the actual graph, but I'll talk about the axes. So we want length of spring on the bottom axis. So we need to go from 0. So if we go up in 5s, 5, 10, 15, 20, 25, that would fit quite nicely there. Okay, and up on the y-axis, we need to get to 7, so that's going to be 2s. 2, 4, 6, 8, like so. And you'll plot the graph, and what you will get is 2 marks, or 1 mark for your scale, 2 marks for your points, 1 mark for your line. State the length of the spring when no force is applied. So from that, you're going to have to work your graph backwards. And what you would get is a length of spring to be 5 when you work your graph backwards. Okay, so decide to connect 2 of these springs in parallel. Means you're going to have twice the spring constant. Spring is attached to that model aeroplane. The 2 spring is stretched to a maximum extension of 15. Use the graph and equation page 2 to calculate the work done stretching the spring system. So the work done is going to be a half fx. So on this graph, we're then going to come up from 15, and that is going to give us 12. So that's going to be a half times 12 times 15 times 10 to the minus 2, which gives us 0.9 joules. Okay, in terms of the marks here, you get 1 for picking the right equation, 1 for the substitution, 1 for that, and 1 for saying joules. Okay, health and safety says it's got to be a maximum speed of 4. Okay, work it out. So if we've got 0.9 joules of kinetic energy, okay, we get that V equals the square root of 2 times energy over mass when you rearrange it. So you get a speed here to be 5.7 meters per second, which is too fast. 3 marks basically is one for rearranging, 1 for realizing that it's 0.9, and 1 for doing this last step here. Why is the actual launch velocity less than what you calculate? The plane has less KE. That's your first mark. The second mark is for saying not all energy is transferred. From spring to plane. Suggests that maximum momentum would be more appropriate than maximum velocity. Explain why this would be an improvement. Well, momentum has mass in it, so momentum, rho, has mass. Oh, not has mass, takes account of mass. So a heavier object with saying, now you can use the word speed here or velocity, I'm going to use speed because it's easier, has more momentum. So more dangerous. Heavier object with the same speed, and the 2 marks basically, one for saying it momentum has mass in it, and the other one is for pointing out that something along those lines. Okay, so thanks for watching. Like I said, that one was I thought they'd be getting better. That one was not quite as good as the one before, but it was a bit shorter. So well done for making it through this far. Good luck with those questions, and hopefully see you on the next one.
Okay, so well done for making it to the end. Thanks for watching it. I know some of these are pretty long. And like I said, if they help, leave us a comment. If they don't help, leave a comment. If you'd rather the review bits, which make them really long, I'll put in separate videos. Again, let me know. It's not a difficult job to do, and I can put them in separate videos rather than putting them in the main video, and it will make basically 2 shorter videos. Please like, please subscribe, and hopefully they help with your qualifications.